and lives at 300 degrees Celsius, 200 kilopascal, while losing heat at rates of 25 kilowatts. So for an inlet area of 800 cm square, determine the velocity and the volume flow rate of the steam at the nozzle's exit. So here we are still dealing with a nozzle. So again, you need to know what to do first. So meaning you need to identify the question. What are the questions? What are things involved in the questions for now? Okay, so first thing first, it will be the first four words here. Meaning, so here, the steam enters a nozzle. So meaning here in this question, we still have a nozzle. Whatever that enters here is steam, so H2O. So this time we are dealing with H2O compared to the previous question where we deal with air. So again, let's denote inlet as 1, outlet as 2. So what we have here is this. T1 equals to 400 degrees Celsius. P1 is 200 kilopascal. And we also know that inlet velocity is 10 meters per second. So, and it leaves at 300 degrees Celsius. P2 is 200 kilopascal. So you are also told that this nozzle will lose heat. Okay, so there is also a Q out at 25 kilowatt. So for an inlet area of 800 cm square, so you also know that A1 is 800 cm square. Determine the velocity and the volume flow rate of the steam at the nozzle exit. Heat is lost from the steam flowing in the nozzle. So the velocity and the volume flow rate at the nozzle exit has been determined. So actually the second paragraph is just a repeat. Alright, so main thing here, these are everything that you are given. So you can see that actually these examples here are all quite generous because you are given quite a lot of things. And so here you need to determine the velocity and volume flow rate. So you need to determine V2 and also volume flow rate 2. Basically same thing actually. Once you found V2, you can find volume flow rate 2, right? Okay, so this one I will just discuss because in general the method is still quite similar to example 1 because it is the same type of system. Okay. Alright, so we move. So here, so this is the second slide. Now, so whatever that's drawn there, I mean the figure here was basically what I draw just now. Maybe with a bit less information. Alright, so we are dealing with steam here. So again, steam is H2O. And always remember, we always start with assumptions. So for this assumption, of course, again, this is an open system. So you always start with the steady flow assumption. And here we say negligible change in PE. Since we are dealing with nozzle, you cannot neglect KE. So no work interaction in this case. Again, like I said, this one not too important. So you also cannot assume ideal gas because we are dealing with H2O here. You can only assume ideal gas for A. Okay, so here taking steam as the system, actually this term a bit weird, but actually taking nozzle as the system is better. So your control volume here, this is the entire system. Okay, so we go through with the open system equation. So once again, it's actually the entire. So Q in plus work in plus m dot. So h1 plus v1 square over 2 plus gz1 then equals to q out, work out, plus m dot h2 plus v2 square over 2 plus gz2. So it is still this entire thing. You cancel off the PE term, cancel off all the work term, and in this case what we have is q out instead of q in, and you are left with this equation. Okay, so again, like I said, don't try to memorize like cases for each of the type of the system. Always start with the general one, then you can solve whichever that are not applicable for the system. Okay, now so this question is slightly different from the first one in the sense. So let's look at the example 1 that we have last week. So example 1 was adiabatic. Oops. So you can see that this was the equation, right? In example 1, this was what we derived. So it was, what we have was only enthalpy as well as Ke. But in this case, what we have here is actually, so here we actually have a Q out term, right? So the difference here is that when you have a Q out term, you cannot cancel off mass flow rate. So meaning that is actually one additional term that you have to find out for this question. Because the previous question you don't need mass flow rate because you can cancel it off. In this case you can't because you have a Q out term. But of course, I mean, this one that you don't really have to do it. My next step, I remove the mass flow rate, but actually I just move it down here lah. It is still there. It's just that we are just rearranging a little bit the equation, but mass flow rate term is still there. So from here, now you can see that based on this question, H1 is what we need to find out H1. We need to find out H2. V2 square is what we need to find in the end. So the information that we need, and then V1 square is given. We have H1, we have H2. And of course, Q out is given. We need to find out mass flow rate. So there are actually 3 things that you need to find out for this question. Right, so H1, H2, M dot, or else you cannot solve this question. So H1 and H2 should be very straightforward for you, because we are dealing with H2O here. Since you are given P1 and T1, you are also given P2 and T2. So H1 and H2 are things that you should be able to find. Okay, for this case. Alright, so now we just move the equation over here. So once again, we are looking for H1, H2, as well as mass flow rates. So these are the 3 things that we need in order for you to find out what is V2 squared. Q out is given, V1 is given. So how do you find H1 and H2? Yeah, so you are dealing with water or steam, H2O. So always remember, H2O, we always find them out from table. So here, you are given P1 and T1. You are also given P2 and T2. Actually, there's a typo here. So this T2. Alright, so from here, you can get H1, you can get H2. This is most probably the superheated water table. Okay, since you're given both pressure and temperature. Okay, so now we're settled, we're done with H1 and H2. How about mass flow rate? So how do we find out mass flow rates?
Equation.
What equation? So always remember one thing. When you're dealing with water or R134A, most of your solution, I won't say all lah, all is a very strong word. Most of your solution will revolve around the table. So the hint is also given here. So think again, how do you find out mass flow rate? So what's the equation for mass flow rate?
I know it's equation.
ME student, what's the equation for mass flow rate? Yeah, so the equation for mass flow rate is rho AV, right? Which in our case, what we have is actually specific volume instead of rho AV, rho lah, which is the same thing, right? So that's why I say the hint is also actually here, because we actually found out what V1 in this case. So there is also one additional information that we didn't we didn't use, which was A1. We were given A1 as well, right? So to find out the mass flow rate of the steam, we use the rho AV equation, or 1 over specific volume AV. So then you sub in the specific volume term, you sub in the area term. So the area given in the question was 800 cm squared. So don't forget to convert it to meter squared. So in this case it's 0.08, then multiply by velocity at the inlet. So from there you can obtain the mass flow rate of the system. Okay, then you substitute the mass flow rate term into the above equation, H1, H2, and also mass flow rate into the above equation, then you will be able to get the velocity at the outlet. So there is still one more thing that we need to find out, which is the volume flow rate at the outlet. Right. So how do we find volume flow rate at the outlet then? Generally, if you think about volume flow rate, it will be AV, right? But we don't really have A2 in this case. Then how do we find the volume flow rate at the outlet? So actually it still comes from the same equation. You move this over here. So you will see that m dot v is AV, right? So which is why here we look for V2, the specific volume 2. So from here you can just use mass flow rate, so because we assume steady flow. Mass flow rate is constant throughout. So you use back the same mass flow rate term, multiply by specific volume at the exit, then you can get the volume flow rate at the exit. So in the same manner, Then from here, you can also find out, let's say if you are asked what is the area of the nozzle at the exit, you can find that out as well from here. Again, using the same equation, but V2 in this case.
How?
Sorry, this one should be W.
The steady flow can you explain?
Can I explain a bit steady flow?
Just how what is it?
That's the major assumption that I said is for open system. So for the entire open system, we assume steady flow process, mass flow rate doesn't change. That's all. Okay, always remember rule of thumb. Closed system, mass doesn't change. Open system, mass flow rate doesn't change. Okay, in our case. Which is the reason why we don't care about energy transfer through mass. Because we always assume that they are the same.
Q 是 H 来的 ，H 的话是在结构那里。
QR is given.
Q 是 given。哪里？因为我们
算不出来的。
So is everyone clear with what we are doing here? You can also check out the V2 and H2 value on your own with the table, just to see if the way that you find the value from the tables are correct. Okay. Alright, then if everyone is okay, then I will move on. Right? Okay, so the next example that we have is actually a compressor. So again, we are still staying at the open system example so that we can look at more open system. So here we have a compressor. So air at 100 kilopascal and 280 kilopascal. So now we are going back with air again. So we're dealing with air, I guess. So is compressed steadily to 600 kilopascal and 400 Kelvin. The mass flow rate of the air is 0.02 kilogram per second. And a heat loss of 16 kilojoule per kg occurs during the process. Assuming the changes in kinetic and potential energy are negligible, determine the necessary power input to the compressor. Alright, so here, this time we have a compressor. So again, like I said, the QA and QR all depends on the question itself actually. So in this case, let's look at this thing again. So once again, we write out the whole thing. So since the question itself told you to just ignore these two things, so we can cancel them off. We are dealing with a compressor here. A compressor supply work to the, so let's say, so like I said, exam, this thing won't be given to you. Okay, you have to be able to imagine this yourself. So a compressor, primary job is to, so and again, when we talk about work out, work in, Q out, Q in, we are primarily talking about the substance. itself. So in this case, meaning we are talking about the air, we're not talking about the compressor. So the job of the compressor is to supply energy to the air. Okay, that's why it can increase the pressure. It is supplying energy to the air and to increase the pressure of the air. So a compressor will have work in, will not have a work out. Okay, work in is the primary thing. And Q will depend on the question itself. So in this case, the question tells you that the compressor loses heat, so meaning it has Q out. So it won't have any Q in. So then if you write out this whole thing, then the equation should be reduced to just this form, which you can find in the next slide lah. So later we will see. So yeah, if you write this equation out yourself, this is what you are supposed to get. Okay, so here again, this question is more straightforward than the previous one, because in this case, Q out is given, and it is actually given in terms of specific heat rather than the actual heat, and then you just need to find out the work in, so necessary power input to the compressor. Alright, so again, same assumption, steady flow, negligible change in K and PE, but this is air, so we can say air is an ideal gas. So we take the entire compressor as a system, and yeah, so you can see this is the same equation that I wrote just now. We pretty much reduce the entire equation into this state, and then we move the m dot h1 over to the right side, and you're left with work in equals to m dot q out plus m dot h2 minus h1. So So from here, then once again, you look at what you need. So for the question, all we need to find out is work in. Mass flow rate is given. Q out is also given. So what you are left with is to look for H2 and H1, which in this case, we are dealing with ideal gas here. So H2 and H1 can be changed into another form, which is, so what can you do with H in this case? Or how do you find H? So once again, the question actually is not very clear in this case, because again, this is just an example, that's why it's okay for it to not be so clear. So when we are dealing with air here, H2 and H1, we have two methods, okay? So one is you just get H value from A17. So table A17, as long as you have temperature, you can find out the enthalpy from the table. So the other method, of course, is to use H equals to CPT. Okay, so again, exam, you are expected to know both of these methods, but exam will let you know which one to use lah. Because both won't give you an exact same value. So I'm not going to just ask you to just guess which method to use. So if it comes out in exam, you will be told clearly which method to use. So in this case, nothing is told by the question here. My answer here actually utilizes the value from table. So again, you go to the table A17, as long as you have temperature, you will be able to get the enthalpy value from the table. Okay, so then you can submit the H value and you will be able to get the work in value. Okay, so this one is a very straightforward solution. Just sub everything in, you get the work term.
题目会写好了用哪个推论？不会，你自己猜自己试试。
So if you try this out with the CPT method, meaning you replace CPT and CPT. So let's say if you use the CP at 280 Kelvin and CP at 400 Kelvin, your answer will probably be slightly different, but not too much. It will still be around 2.7 kilowatt. Alright, then we move on. So this next example, then I let you try. Okay, so here we have a condenser this time. Again, it's still another open system example, but this time we are dealing with a condenser. Okay, this question asks you to use R1348. Okay, so different table, but it is still a table. So we have R1348. Actually, we have two things, sorry. To be cooled by water in a condenser. So the refrigerant enters the condenser with a mass flow rate of 6 kg per minute at 1 megapascal and 70 degrees Celsius and leaves at 35 degrees Celsius. So you can also see that in the diagram or the figure given. The cooling water enters at 300 kilopascal and 15 degrees Celsius and leaves at 25 degrees Celsius. So neglecting any pressure drops, determine the mass flow rate of the cooling water required, and B, the heat transfer rate from the refrigerant to water. So you are expected to determine these two things. Try to solve this. See how you can approach this. So we have a condenser here. So essentially this is also a heat exchanger, to be more precise. So let's call, to make things simpler, let's call m dot r as the mass flow rate of the refrigerant, m dot w is the mass flow rate of the water. So you need to find out m dot w.
open system is a closed system. You open, don't open that. 这是 closed system， open system。你看，我都会看，我都会看。这个明显没有看错。应该没有给图画上平时。好的。你先会看的，你先看个错一下。
So don't forget that you have two different substances here. So when you are using the table, you need to use two different tables.
So MR jadi enggak dia kan so NW nó chẳng đi hết được nhé chẳng đi hết đi theo MR冷气的水没抽流的冷气水。好像蓝色不会是。好像比灰还能冷。Chúng con sẽ đi theo cái tông thật theo cái là miệng màu thật bạo màu à chân mình hình thay thật chân mình nó không giống sao chân不是chân mình nó không松抽不给我，松抽给正。有它的亲笔签名盒。还有蓝色安全。
越洗越这样黑。
厉害。到4大站。 你成为了牛仔裤的老板娘，还是1年洗一次？我脸其实不很脏的，可能你把它越洗越安排。因为它国家很少人看。发表为什么灯？他不是发条子看电话？刚才我看到现在发的。是PV 翻烫完了。哦，太厉害！菊花不老。哦，可以 get 出来，还是有。可能有点心理层面。然后健康。台湾有一个，没吧？CIA 有个。训练。
Alright, let's discuss this question and see if you get this correctly or the same. Now, when you solve this question, there is, especially when you are solving both A and because you need to solve both A and B. Now, this question you need to go back to the basic a little bit in the sense that we have to choose what system that we are analyzing. Okay, what do I mean by that? It will be a bit clearer later when we discuss the whole thing. So for now, we do the usual thing. Usually system will just take the whole thing that the question shows us, right? So here, we take the entire heat exchanger as the system. So meaning, this whole thing here, oops, sorry. So this entire thing is our system. Okay, so when we take this whole heat exchanger as our system, so our energy balance. So again, bear with me, I will just write out the whole thing. So Q in plus work in plus m dot H1 plus KE1 plus PE1 equals to Q out plus work out plus m dot H2 KE2 plus PE2. So as usual, these two we can cancel off. H is something that we never cancel off. Okay, unless the question tell you H is constant lah. But in that case, it's not actually cancelled, more like they just minus off each other. Now, do we have any work in or work out in this case? No, right? Because this is just a heat exchanger. How about Q in and Q out? If you are taking the entire thing as the system, Q in and Q out is also negligible, as in unless the question tells you the system is losing heat, because the heat exchange takes place within the system itself. So what I'm trying to say is this. So R134A is cooled by the water. So meaning R134A is rejecting heat to the water. Okay, maybe I don't write out Q, I just write Q. But everything, all the heat transfer occurs within the system itself. They don't go across the boundary. So meaning, again, we are assuming that this whole thing is adiabatic. So for this question, actually that can be one of the assumptions. So we cancel Q in and Q out. So what you are left with is m dot H. Maybe in this case, I write in better lah. Too many number. Okay. So what we are left with is m dot H in and m dot H out. But these two things, we can further expand a little bit. The H in, enthalpy in, is actually m dot R H3. This is the refrigerant inlet. And m dot W H1. Then out will be m dot R H4 m dot W H2. Does it make sense to you? So you have your inlet here, you have your inlet here. Let's change the color. Then, so inlet is the red one, then outlet is the blue one. So these are your outlets. These are inlet. Okay, so does this make sense to you? Any questions that you want to ask here? So this is just what I write lah. So later again in the slide I will repeat this again. So now I'm just teaching this step by step. Okay, so essentially this is still energy in equals to energy out. But the energy in here will be entirely the enthalpy of the water and the R134A. Energy out is also the enthalpy out of the water and R134A. Okay, so this is what happens when you take the whole thing as the system. Okay, so we go to the next slide first. So assumption here, yeah, so you can see the usual steady flow process, negligible change in K and PE. Heat losses from system are negligible, so that's what I was saying just now. Then there is no work interaction here. So we take the entire heat exchanger as a system, which was what I said. Then, okay, so this one, I kind of neglect to say this, but I think it was understood lah. The whole thing was steady flow process. So we are saying that at 1 and 2, so 1 and 2 was the inlet and outlet of the water. The mass flow is constant, which is m dot w. That's what I defined just now. M dot 3 and 4, inlet and outlet of the R134A. So we say that it is m dot r, which is the mass flow of the refrigerant. So we define these two beforehand, but of course this is the more proper version. We are saying steady flow, so mass flow in equals mass flow out. Okay, so I think this one so far shouldn't be an issue. So then, our energy balance. So, energy balance, you are left with this equation. So this was what I derived just now. You move, so we move all the water term to the left or right, doesn't matter lah. You move all the water term to one side, all the refrigerants term to another side. So then you got this equation. So essentially, what we are doing here, if you just look at this equation, right, you will see that we are basically just saying that, never mind, I will talk about this later. Okay, so now we got this equation. So meaning we can start to solve this question, right? We need to find out mass flow rate of the water. We need to find out the mass flow rate of the we need to find out mass flow of water. We have mass flow of the refrigerants. So once again, we are back to looking for all the enthalpy value. So for the water, which is for H1 and H2, so both of the water, if you just check the states that you are given. So in this case, 15 degrees Celsius and 300 kilopascal, that's the inlet. And since we assume no pressure drop, outlet is also 300 kilopascal, 25 degrees Celsius. At such a high pressure, if you just look at the temperature, you actually should know that it is compressed liquid lah. Because at 100 degrees Celsius, these are compressed liquid. So at 300 degrees Celsius, they definitely will be compressed liquid, because saturated temperature and pressure increase with each other, right? So these are compressed liquid. So for compressed liquid, you can just approximate them as saturated liquid at the temperature. So then you can get H1 and H2. So technically speaking, okay, never mind. Again, I'll say this later. So you get H1, H2 here. Alright, so everyone understood how we get H1, H2 here? Then we proceed to H4 and H3. So for H4 and H3, then it's slightly complicated because we are dealing with R134A here. So you go to R134A, you check the pressure and temperature. Then these two are actually at different states. So for R134A, this is actually a superheated vapor. Don't write superheated water. You can write superheated refrigerant, but not water, because now we are dealing with R134A. And this is actually compressed liquid. So they have completely different saturated temperature compared to water. So at this one, you can see that at 70 degrees Celsius is already a superheated vapor. This is also why we choose to use refrigerants for like aircon system, because then they have different vapor, they have different boiling point. Then we can use them, like they evaporate easier. Then it is easier for us to transfer heat. So as you know, latent heat is much higher than just normal temperature heat transfer, like normal temperature change. True. So okay, clear so far? Right, so then after that I realized my slide actually stops here, so I don't really have further things. So after this I will just write them out because yeah, I didn't know why I just stopped here. But anyway, you can actually solve the mass flow rate of the water, right? So now you sub in H1, H2, H3, H4, you can get mass flow rate of the water. I'm not sure what's the value, but yeah, basically sub all these things into the equation, you can get m dot W. Right? Then let's go back to the question again. So question part B asks for heat transfer rate from the refrigerant to water. Okay, so you need to find the Q out of the refrigerant. So in this case, right, actually it is a very straightforward solution here. You actually have found the answer, right? Can you see where have you found the answer? So now let's say, so this is a heat exchanger, okay? Then we have this. So in this case, right, let's say we take this as our system this time. Okay, so we take the heat pipe as our system. So we don't take the whole thing now. So the heat pipe is the one where R134 is flowing, right? So if you write out the whole equation, sorry, this time I won't write out the whole equation, but if you cancel off, what you are left with is actually Q. Okay, never mind. Let's write out. No. So Q in plus work in plus m dot H3. I don't write K and P this time. Okay, easier. So work out plus m dot H4. So this is the heat transfer from the refrigerant. No, sorry. So this now we are only looking at the heat pipe. So for the heat pipe is being cooled by the water. So meaning the heat pipe is losing heat, right? So always remember, we don't have such thing as coolness. Cool is not a type of energy. We only have heat. So when we cool something down, which it actually means that we are taking heat away from the system. Right, so it's Q out, Q in we cancel off. Again, we cancel work in, we cancel work out. So Q out, you rearrange, what you get is H3 minus H4, which is actually here. This is H4 minus H3. But doesn't matter. The sign itself it will cancel off eventually. Okay, so this is the Q out term in this case. So in the same manner, right, let's say if you take the system over at the water side, what you will be left with is actually Q in equals to m dot H2 minus H1 water. Right? So let's say, so we say that we assume no heat loss, so the entire heat from the heat pipe goes into the water. Entire heat from the refrigerant goes to the water. So which is why if you equate these two things, you are just getting back this equation. But the other way around lah, the sign doesn't matter because they will cancel. Can you see that? You are actually just getting back this equation here. So just different perspective. So we choose different system, you get different answer, essentially. Right, so for this question, of course, for part B, what you want is this one. So you just submit the value, you find out Q out. So this is also actually something that if the syllabus haven't changed for like 17, 18 years lah, and if I remember correctly lah, you sort of have learned this in secondary school before. When you do heat exchange, you do, but that time instead of H, you do MC delta T, then like you do MC delta T equals to MC delta T, then you find out what is the change in temperature. Right, you have learned this like long time ago, for me even longer ago time. Right, so it's actually the same thing. So you see, if we sub this whole question with air, then you will be solving this in terms of MC delta T. But so just one thing, remember one thing, for us water, we don't really use CP delta T unless the question asks you to. So stick to the table. Everything use the table value, don't use MC delta T. So this one actually is the same thing as MC delta T that you have learned. So if it's air, then yeah, this will work. It's the same thing. Okay, so everyone clear here, right? Then now move on. Okay. So the next example is actually something easier. We go back to something simpler. So chapter 2 and 3 here. So like I said, this is actually kind of a revision slide. Basically, we are just looking at things for the first half of the lecture before the test. So this, we go back to a simpler time when we don't really have all this enthalpy, internal energy. So here we are looking at the windmills, okay? So a windmill slow the air and cause it to fill a larger channel as it passes through the blades. So consider a circular windmill. Actually, this is still an open system because we're talking about a windmill. Consider a circular windmill with 7-meter diameter rotor in a 10-meter second wind on the day when atmospheric pressure is 100 kilopascal. So let's say this is 1, this is 2. Okay, as usual. So here we will have so this is 7 meter, and we know that V1 is 10 meter per second, P1 is 100 kilopascal, and T1 is 20 degrees Celsius. The wind speed behind the windmill is measured at 9 meter per second, so V2 is 9 meter per second. Determine the diameter of the wind channel downstream. So you need to know what is the wind channel downstream, the flow channel size. So you are looking for actually D2. This is D1. And the power produced by this windmill. So you need to find out what's the power produced, presuming that the air is incompressible. So this time we assume incompressible air. So now, even though I say we go back to like older chapter where we don't really care about enthalpy and internal energy and stuff, technically that's not correct in a sense. It's just that, like in this kind of example, let's say we have windmill. In most cases, when a windmill operates, it does change the pressure a little bit, but it doesn't really change the temperature of the air, right? So essentially, if air enters at 20 degrees Celsius, when it leaves, it is actually supposed to be T, so that, like let's say in this case, T2 is supposed to be about 20 degrees Celsius as well. Because technically speaking, the windmill won't really change. It won't have large enough change in energy to change the temperature. So when temperature doesn't change, enthalpy doesn't change. So it is still the same type of question, it's just that we are neglecting those terms, that's all. Okay, so this question is actually very straightforward. Essentially, the change of the energy here will be a result of the change in the velocity. Basically that we are converting kinetic energy to work output. Okay, so the flow of air through a flow channel is considered. The diameter of the wind channel downstream from the rotor and the power produced by the windmill are to be determined. So now this is the type of solution that I don't like for now. But let's see what we do here. Okay, so first off, the question actually used, so because we are dealing with air here, which is ideal gas, the air uses the ideal gas equation. So we use the ideal gas equation based on the temperature and the pressure. We found out the specific volume of the air. So the question tells you that this is incompressible. So based on the specific volume of the air, you can actually just find out what is the diameter downstream. Okay, because if so incompressible case, volume flow rate 1 will be equals to volume flow rate 2. Okay, so from there you can find out so for now actually we found this, but we are not using it. Basically we are just using A1 V1 A2 V2. Based on this you can find out what is D2, so the diameter of the wind channel downstream. So this one should be very straightforward. Okay, so then from here, and based on the specific volume, you can actually find out the mass flow rate. So why do we need the mass flow rate? Because we are looking for the power produced. So always remember this. I mentioned this a few times before this. Whenever the question say, find out what is the power, what are the heat, if it doesn't specifically use the term specific or like per unit mass and stuff, we are always looking for them in terms of watt or joule. It is never in terms of per kg. Okay. So in this case, then we want the power produced by the windmill, which is just the kinetic energy term. Then you can get the answer. So again, essentially, let's say we are talking about this in terms of open system, okay? We can actually still use back this equation to solve for this question. It's the same thing actually. It's just that we need to make as much assumption as previously done. So here, of course, PE we can cancel off. We assume adiabatic system, since the question also didn't tell you anything. Since this is a windmill will generate work, meaning it is taking the work term, the energy out from the air. So we have work out instead of work in. Windmill is essentially a turbine, but a very slow one. KE and PE we cannot cancel off because the question does tell you that we have V1 in, V2 out. So the one that is a bit ambiguous is basically the enthalpy term. So like I said, here we need to use a bit of common sense. So let's say we have a windmill. You have a normal windmill, and it has a very big channel in this case. So the change in the temperature is actually very negligible. Essentially, the only change is because this is also incompressible. So the pressure probably will change a bit, but then negligible. If temperature doesn't change, again, if temperature doesn't change, these two will just cancel off. So that's why we are left with work equals to the change in kinetic energy. So maybe if it is a channel, it might not look so logical to you. So let's say if you just look at a normal windmill on top of a hill, before and after the windmill, definitely temperature and pressure won't change, right? No matter how the wind change, so enthalpy will change in that case. So the energy that you extract is just KE.
对，它是 KE 不要看错。
Or the R you have to get from table. Is it in the exam, right? It's there one, like it's in the table. The table is there, so for in your exam. Or you memorize for A is 0.287. This is the standard value.
So how much is it? I can自己用闹出个钉钉的去。然后不是先创了。
So usually, like when I solve this, actually the working will be sort of the other way around. Because like what I showed you just now, I usually like to write out the full equation first, then we see what we need to find out. Because like in this case, right, like this example here, the answer here is just the same as all those solutions that you have so far. Because the question knows what they are looking for, so they just find out all these terms first. But like for you, you probably won't know that at first that no, I need to find out what's specific volume, and and other stuff. So write out the equation that you need first, then you look slowly at what you need to find out to put into that equation. Like what I did in the previous 2 examples or 3 examples. Okay, so this one, is everyone done? I'll move on. Okay, so now we look at, so again, like I said, this revision, so we go back to closed system, right? So now we look at a simple closed system question. Saturated water vapor at 200 degrees Celsius is isothermally condensed to a saturated liquid in a piston cylinder device. Calculate the heat transfer and the work done during this process. So, very straightforward question. You are given saturated water vapor at 200 degrees Celsius and final state saturated liquid. We have a piston cylinder device, so it's a closed system. Now, so even if the question doesn't tell you that this is an isothermal process, you should know that this is an isothermal process as well, because the water basically changed from saturated vapor to saturated liquid. This is a condensation process, right? So it is isothermal, but no, we do have the information here. Of course, maybe in some cases we are maybe condensing it at different pressure, then it changes, then maybe it won't be isothermal, but mostly it is. So here you need to calculate what is the heat transfer as well as the work done during this process in kilojoule per kg, because in this case we don't know what's the mass. So you are asked to find out in this sense. So now that we are back to closed system, how do we start solving this question? What do we start with? Closed system. How do we start solving closed system? Closed system. What is the basic equation that you need? You write here. So for closed system, this will be Q minus W equals to U, or change in U. So this is what we are dealing with here. And of course, if you want, you can further expand the Q and W lah. But here, let's say let's say we don't know what are the Q and W here, okay? So as in, we are not very sure whether we have Q in or Q out. Of course, we know that it's Q out lah. It's written in the question there. And also, let's say we do not know whether this is a work in or work out. But one thing that you can bear in mind, these two will always be the opposite of each other, unless you have more than one work or more than one heat. Because you cannot have only energy in, you cannot also only have energy out. They will always balance each other out. But unless, of course, if you have two work or two Q, then that one may be a bit different question. So like in this case, so one of them will definitely be in, the other one will definitely be out. So then, if from the question we can see that actually we have a work, we definitely will have a Q out lah, because this is a condensation process. Then where does the work come from? What is the work in this case? Boundary work. Okay, closed system, you always have boundary work, don't forget this. So boundary work can be either a compression work or expansion work, depending on whether the piston is going down or going up. So again, like I said, if this heat is going out, boundary work is most probably going in, so work in. But again, we just keep it as Q minus W first, general term. We just pretend like we don't know which one it is. Alright, so of course, first thing that we need to find is delta U. Delta U is something that we can find because we do know the initial and final state of the water. We have two information as well. We have temperature, you also know what is the phase. Okay, let's see. So here, I think my solution is also using the general equation. So this general equation is actually Q minus W equals delta U, but yeah, don't forget that we actually have these two terms lah. It's just that usually we assume stationary system. So these two are also negligible, so can cancel off. But essentially it's just Q minus W equals delta U. So first we find what are the values for U. Specific volume, not sure why we need them yet, so we don't care. So let's say in your case, you probably won't find the specific volume first. Alright? So from the table, you can find out what is the V1. So V1 is actually saturated vapor. So essentially saturated vapor is also X equals to 1 lah. Oops. So this one is saturated vapor. Okay, so in case you are not aware, X equals to 1 is saturated vapor. And then we know that final state is saturated liquid. Okay, so from here we can obtain U1 and U2. So one is UG, one is UF. You can also see what is the pressure, what is the pressure during these two states. So this is actually just saturated pressure at 200 degrees Celsius, because we are dealing with saturated state here. Okay, so from here, then we are done with the right hand side of the equation, which is delta U side. Because we have U2, we have U1, so that's settled. Now we are left with, so we still have two variables, right? Because again, let me rewrite this so that it's easier to see. Q minus W equals to U. We are looking for them in terms of kilojoule per kg, so the small letter term. Now we are done with this. We are done with delta U because we have found U1 and U2. But we still have two variables on the left, Q and W. How do we solve this? Or rather, which one can we find first? Can we find Q? Can we find work? It's either one of them, right? Q or work. Again, actually all the information are on the screen now, it's just that you don't know yet. Alright, so this question is intentionally tricky in one sense. It tells you this is an isothermal process, right? But if it is an isothermal condensation process, it also means that it's actually an isobaric condensation process. Because throughout the process, it is just saturated state. So temperature doesn't change, pressure also won't change, right? So if we have an isobaric process, can we find the boundary work? We can find the boundary work through P delta V if you have an isobaric process. So you can use P delta V here. So the delta V in this case is the small v because we are looking for the answer in terms of per kg. So you use this V2 and V1. You minus them off, you multiply by the pressure, you can get the boundary work. So the boundary work that you found will actually be in terms of negative because, like we said just now, we speculated that you will get a work in, right? So work in term is negative. So once you get this value, you sub this into this equation. So when you keep the entire thing in the general form, so this is the general form, then when you sub in the value, make sure that you sub in the unit as well. So then you sub in the work term into the equation, you get the Q term. So Q term will also be just negative in this case because we know that the system is losing heat. Again, just to clarify, this is actually so this is actually the small v, okay? It's not the big V. Because we only have the specific volume, we don't have the actual volume. So this one is actually small v. That's why your answer is in terms of kilojoule per kg. If it is a capital letter V, then it is kilojoule. Then it won't be kilo per kilogram.
Work in 就是 negative 不是
So let's say if you're asked to draw a graph, TV graph, then it will just look like this, right? So 1 and 2. And let's say if this is a PV graph, it is actually the exact same graph. Okay, because whatever happens there is the same thing. So PV graph, this will also be an isobaric, isobaric process, so it is still the same thing. So let's say if we say this is a PV graph, then boundary work is simply area under the curve. So that's where we got the equation. So this is work boundary. So we have one last example. So after this one, then we are done. Okay. So here I think it's one last. Yeah, it is one last example. So here, this is another closed system question, but we use a slightly different type of closed system. So closed system, again, like I said, in general, you only have two types of closed system. Okay. So you either have a piston cylinder device, or you either have a rigid tank. So rigid tank, then mostly you won't have any boundary work. Piston cylinder device, yes. So here we have a well-insulated rigid tank, which contains 2 kg of saturated liquid vapor mixture of water at 150 kilopascal. So initially, 3/4 of the mass is in the liquid phase. So this is actually important information. An electric resistor placed in the tank is connected to a 110 volt source, and a current of 8 ampere flows through the resistor when the switch is turned on. Determine how long it will take to vaporize all the liquid in the tank. Also, show the process on a TV diagram with respect to saturation lines. Okay, simple question here. What is the initial quality of the water? So initially, you know that we have a mixture at 150 kilopascal. Then they tells us, so like I said, simple question because it's in the question. 3/4 of the mass is in liquid phase. So meaning what's the quality? What's X1? So you need to know that in order for you to solve this question, right? So if 3/4 of the mass is in the liquid phase, X is a measure of the vapor, amount of vapor. So X is just 1/4, 1/4. So 0.25. So initially X1 is 0.25. And also again, same thing, this one you can always start with just Q minus W equals to U. In this case, we can use the capital version because you are given the mass flow, the mass, right? So it is a well-insulated tank, meaning this get cancelled off because there's no heat transfer through this system. And we know that in this case, we are supplying work or energy to the system because, yeah, very obviously that we have a electrical resistor. So meaning here, work then work in equals to U. So what you get is actually work in equals to U2 minus U1. Basically, this is what we have. So this is the equation that you have to work with. You have for you to work with. Okay, so now if you are not very sure, again, here this is where this is the minimum that you should be able to reach. Okay, so then after that, of course you need to figure out what are the two states that you are dealing with. So state 1, we have 150 kilopascal, a mixture with quality 0.25. Then state 2, you are told that you need to find the time required to vaporize all the liquid. So essentially we are saying that phase 2 or state 2, we have a saturated vapor. That's what the question is saying. Okay, so let's look at how we can solve this. Okay, the last part of the question say draw this on a PV diagram. I have the answer here, but ignore it first. Alright, so like I said, so this is what we derived just now, right? You can ignore the in and out, but essentially, yeah, when we write this general equation, we are assuming that we are having Q in and work out. You can just ignore it and just say that it's Q minus W first. Then when you submit work in, then it becomes positive. That was what I wrote just now. So then the work in term, we know that it comes from the electricity, right? The resistor. So the resistor will be V I and how long it operates. Vi is power, then delta T is the time. So delta T is what we are looking for in this case. So delta T is what we are looking for in this case. Then we have V, we have I, mass is given, then again we just need to find out what is U2 and U1. So for U1, we know that P1 is 150 kilopascal, X1 is 0.25. You can find, we can find out that from the table, this is the UF value, this is the UFG value. Why do I need the specific volume value? I have no idea. We continue first. Okay, so from here, based on our general equation for mixture, you can find out what is the initial internal energy as well as internal specific volume, which again, I still feel like you don't actually need a specific volume, it's just extra here. At least as of now, I'm not aware why I need it. I cannot think of a situation where I need it as of now. Okay, so from here, what you need is actually U. Okay, so from the table again, for mixture, you need UF and UFG value. Then based on the quality, in this case, we know that quality is 0.25. So always remember quality is for the fraction of vapor, not liquid. So in this case, liquid is 3/4, so 1/4 is for the vapor. So from here, you can find out what is U1. Then U2 is also very straightforward because we know that it is going to end as a saturated vapor because we want the time for it to be fully vaporized. So the point where everything has vaporized is the point that we are looking for. So saturated vapor. So all you need is actually UG value. Later we'll see lah. Or you can just if you are lazy, you can just sum up these two values, then you will get UG also. The UF plus UFG is UG. Okay, so then anyway, again, like I said, ignore the TV graph first because you are supposed to draw it later. Alright, so we go to the next slide now. So next slide, like I said, okay, now I see why I need the volume, but so anyway, for the second state, we know that the volume doesn't change because this is a rigid tank. Okay, so now again, let's come back to this. So, sorry, just now I said something wrong because for some reason I assume that the pressure stay constant, which is not going to be the case in this case because you are supplying heat to the system, the pressure won't be the same. So the question also never mentioned anything about that. So again, something a bit wrong here. So again, so here the question says that at first we have 150 kilopascal saturated liquid vapor mixture, and we basically turn on the resistor heater, it will evaporate the liquid in the tank. So during that change, during the evaporation process, now usually during the evaporation process, V will actually change because it is changing phase, right? But in our case, V cannot change because you have a rigid tank, volume doesn't change, mass doesn't change, so specific volume cannot change. So if that doesn't change, that meaning pressure is the one that changes lah. Okay, so So, which is why in the first state, we know, so here we know that V2 is equal to V1. So which also mean that small v2 is small v1. So which is why we look for this small v1 here. Okay, so once you have found this small v1, then for state 2, we equate v2 equals to v1. Then we know that it is a saturated vapor. So again, this is the very typical case of we do not know everything about state 2. The only thing that for state 2 that we know is saturated vapor. So we need to find out ourselves what is the second properties that we have for state 2. So in this case, rigid tank, volume doesn't change. So usually rigid tank and volume, these two things, they always come together one lah, because it doesn't change, right? So here we know that V2 equals to V1. Then from here, okay, this one skip a bit steps, but this will be complicated lah. So U2 equals to V1 equals to V2, you know, is saturated vapor. So you need to go to the table. So this one maybe I show you a bit lah. So essentially what you do here is this. So we keep it at pressure. Actually, it doesn't matter whether, again, it doesn't matter whether you are using table, temperature or pressure table, okay? But since the question, we never really deal with temperature at all, let's just look at pressure. So what we have here is 0.29065 Vg, okay? So this is actually a this is actually a Vg value because we know that it is saturated vapor at this state. So you 0.29065. So you have to look through all the Vg value here. So 0.29065 is between these two states. So it's between 650 and 700 kilopascal. Now, it is not necessary for you to find out what is the pressure if the question never asks you. In this case, what we are looking for is internal energy, which is Ug. Right? So, internal energy is in this column, the third one. So, we just go down here. So, you have to interpolate between this Vg and this Vg, and also this Ug and this Ug. So this will give you U2. Okay, so here that's how they get U2. So that's why we also say here, yeah, we never really write this, but you can see here we have a new way of writing, which is Ug at 0.29065 meter cube per kg, because that's the information that we have. Okay, so then the pressure in this case can be found by interpolation as well. So both of them are interpolation. So this is also interpolation. So if the question asks for pressure, actually did the question ask for pressure? Let's see. No, actually the question only asks for the time. But doesn't matter. So let's say if the question asks for the pressure, then you can interpolate between them. You can get the value here. Never forget the unit like me. Always write a unit, okay? Alright, so then you get U2, you can sub the entire in U1, U2, mass, ampere, voltage, current and voltage, then you can get the time. So the time that you get is in terms of second, you can convert it to minute, but if the question never asks for it, don't need to convert. Okay? So now lastly, then we go back to the diagram. So when you are asked to draw a TV diagram, in this case, we know that the pressure changes. So you draw the two. So here you can see we draw the two constant pressure line. So probably, yeah, if you find out the pressure, then you can label the pressure line as well. So this question is slightly different from what you practice in tutorial, whereby your state 1, you cannot simply start. It's better actually if you start from state 2. Why is that the case? Because we know that volume doesn't change. So it has to be a straight vertical line, a linear vertical line. Then state 2, and state 2 has a very fixed location. because state 2 has to be a saturated vapor. So that's why it is better if you start from state 2, then you go all the way down, then you draw the arrow up. So even though state 1 doesn't really look like 0.25, this one is okay lah, because the actual curve itself is actually very large. The distance can be very large. Then it will look like 0.25, but when you sketch, you usually won't sketch that big, so that one is fine. As long as you show that state 1 is a mixture, then that's good enough. So can everyone understand this question? Anything that you don't understand? Any question? If not, then yeah, we are done for today. Then Thursday we will enter slightly into second law chapter. So just part of it. Then yeah, reminder that next Tuesday is your test. Don't be late. Okay, so a bit about the lab, since a few of you asked me as well. Lab is a lab report. Lab is a group report, okay? So as of now, I will only assign I will assign the submission page to the first person in the group, unless the first name lah. Unless you don't like the person, you can tell me, or you think that he is not suitable for the job, or if he never appear for your lab, then I will assign to the second person. Okay, so yeah. So the rest of you won't be able to see the submission page, okay? So you just check with your groupmate. In your group, only one person will see the submission page. I normally will only assign during the second week of your lab, the first or second week. If you have done your lab, that week have passed, you still haven't seen a submission page, then check with me again. Okay? Alright, that's all for today.